Hello students, today we are going to start the chapter current electricity. Whenever current flow to the electrical circuit, then we have to see the different devices and their application in this chapter. Now this chapter starts with the Kirchoff's laws of electrical network. Now these Kirchoff's laws are applicable to closed electrical network only. If you remember, we have seen the semiconductor devices chapter. At that chapter, if you remember, we have used the Kirchoff's voltage law or Kirchoff's second law. At that time I have told you that we will see later on. Now this is the right time to see what is meant by the Kirchoff's law. Now before going into details of the Kirchoff's law, it is very essential to learn the basic concept of the Kirchoff's law, and the basic concepts are nothing but what? You must able to know the junction. So let's see the first junction. So this junction means what? It is a point in an electrical circuit where two or more than two branches combine together at single point. Junction is a point in any electrical circuit where two or more than two branches combine together. If you see here, this I have shown it as small a. At this point, the three branches are coming together. So this A is said to be the junction. Apart from this, at the bottom also exactly opposite, B is a point where more than two branches join together. So this B or A, such type of point in any electrical network is said to be the junction. After that, we have to see the loop. What is meant by loop? Loop, if you remember, in the superposition of wave, we have learned that loop means what? The closed formation of wave, loop-like structure of wave. So same thing in electrical network. What is meant by loop? The closed structure. Suppose we start here and just go here like this. Again come back to this point. So it is a closed loop. That is said to be complete circular loop. Circular or any shape of loop is there. The circuit merge get complete. Start from the same point, again come to the same point. This is one loop. This is another loop. Okay, another loop. You can go like this or you can come like this. And third loop is a bigger one. So this is the closed loop in electrical circuit. Apart from this, we have to see the branches. The branches are nothing but what? The different parameters. Just if you see, this is the first. If you go from A along this side, this is the first branch. Okay, if you go along this side, like from A, go to this side, this is second branch. And we can go either downward direction, that is third branch. Three different, two or more than two electrical connections that are joined together, that is a junction. And that electrical connection which get joined here, one path, two path and T path, third path, they are said to be the branches of electrical network. Now this is about the introductory part. Now let's go to the Kirchoff's law. Now basically there are two types of Kirchoff's law. There are two types of Kirchoff's law. So let's start with the Kirchoff's law. So there are two types of Kirchoff's law. In that two types of Kirchoff's law, there are two types of Kirchoff's law. The first law of Kirchoff, it is said to be Kirchoff's first law, or sometime it is said to be Kirchoff's current law. Second law of Kirchoff is said to be Kirchoff's voltage law, or sometime it is said to be Kirchoff's second law. So let's start with the Kirchoff's first law. So Kirchoff's first law. So let's start with the first law. Or it is said to be what? What I have told you, it is said to be current law. Kirchoff's current law, and sometime it is said Kirchoff's current law, KCL. Kirchoff's current law or Kirchoff's first law. What exactly this says? The Kirchoff's first law says that algebraic sum of the current arriving or leaving from the junction is always equal to 0. Algebraic sum of the current leaving from the junction or arriving toward the junction is always equal to 0, and that is said to be Kirchoff's law. Mathematically, it will be represented by summation of I varies from 1 to n, I suffix I. Means it is what? I1 plus I2 plus so on up to In. So it is what? Summation of all the current flowing. So that means addition of all. Now here, before going into detail of this, again there are some sign convention that must be considered before applying this law to electrical circuit. So what are the sign convention? Let us imagine that at the junction you are standing. At the junction you are standing, and current coming toward the junction, consider this as a positive. Current leaving from the junction, consider it as a negative. I will tell you. That are the sign convention. Suppose this is junction. Let us draw the lines like this. These are the different branches, suppose. So here there are different currents. Let's start with this. Such type of thing is there, and suppose I had on again another branch. So this would be the things. Suppose this is the first current I1, it is I2, it is I3, it is I4, it is I5, it is I6, it is I7, and this is I8. In your book they have taken only 6, I have taken 8, doesn't matter. Okay, now see, suppose at this junction, this is junction where these branches of electrical circuit combine together. So this is junction. So this current coming toward the junction, I1 is going toward the junction, I8 going away from the junction. So if we add all the currents together, the algebraic sum of all this current is equal to 0, and that is nothing but a Kirchoff's first law, or it is said to be current law. But here the sign convention, you should use the current which is coming toward the junction. This current I1, it is always taken as positive because it is coming toward the junction, positive. The current which going away from the junction, just like I8, it is always negative. That sign convention we have to use. It is very simple to remember. Just imagine we are standing here at the junction. The money coming to our pocket, it is positive for us. Money going away from our pocket, it is said to be negative. So this, just assume that you are standing at the junction. Current is coming means what? Money is coming in our pocket. So our pocket becomes positive. Current is going, money is going from our wallet or pocket means what? It is negative. That is a simple thing to remember. Now start with this. What we can write? Just apply that law here and rewrite the equation. So we can write here. So I1 is going toward the junction, positive. I2 again going toward, so it is plus I2. I3 going inside, plus I3. I4 going outside, minus I4. I5 going inside toward the junction, so it is plus. I6 going away, so it is minus. I7 going toward, so it is plus. I8 going outward, so it is minus, and this is equal to 0. This is equal to 0. If you consider this 1, this is 2, and this is 3. 4, 6 and 8. I4, I6 and I8 are the current going away from the junction. So you can write a simple equation from this. Just take a positive to one side, I1 plus I2 plus I3 plus I5 plus I7, and move all this negative to right hand side to the 0 side. So you can write this equal to I4 plus I6 plus I8. So this is a modified form. If you consider this part, okay, I1, I2, I3 like this, thus current arriving toward the junction. I4, 6, 8, see 4, 6, 8, current leaving from the junction. From this you can say that the algebraic sum of the current arrive at the junction is equal to algebraic sum of the current leaving away from the junction. This is an alternative statement you can make for Kirchoff's current law. The algebraic sum of the current entering toward the junction must be equal to algebraic sum of the current leaving to the junction, or simple way, sum of all current is always equal to 0. Algebraic sum of all current coming toward or going away from the junction is always equal to 0, and that is said to be Kirchoff's first law, as it will give the relation with the current, so it is said to be Kirchoff's current law. Again, apart from this Kirchoff's current law is in accordance with law of conservation of energy. See, coming toward equal to going away, so it is equivalent to law of conservation of energy. Now let's go to the Kirchoff's second law, or it is said to be Kirchoff's voltage law. What exactly this voltage law says? That is Kirchoff's second law, or sometimes said to be voltage law. So this is the Kirchoff's second law we have to see. Let's start with the Kirchoff's voltage law, KVL, or simply voltage law. As its name suggests that it is Kirchoff's voltage law, so it must be related to something that is said to be voltage. What this law says? This law says that algebraic sum of potential difference and EMF across any closed loop is always equal to 0. For any closed loop, we have learned what is one loop, the closed electrical circuit. The Kirchoff's voltage law says that algebraic sum of potential and EMF across the closed loop is equal to 0. Potential means what? According to Ohm's law, we know V equal to IR. V is said to be potential. It is product of current into resistance. So this law says that algebraic sum, so I into R plus algebraic sum of EMF. So EI, I varies from 1 to N, I varies from 1 to N. So II suffix RI. In general, you can write like this, and this is equal to 0. That is said to be Kirchoff's second law. Algebraic sum of potential difference and the EMF is always equal to 0. Is that clear? So in your book they have not used a summation, but I have used a summation because algebraic sum it is. So it is one of the same thing. You can use either the summation or simply IR plus EI equal to 0. EI is EMF, all the EMF, sum of all EMF. IR is what? Sum of all potential drop, and this all equal to 0. Now here again there are some sign conventions. So what are the sign conventions that we have to see? What are the sign conventions that we have to see? Initially in Kirchoff's current law we have seen current coming toward a junction positive, leaving away from the junction negative. Similarly here there are some law, or this law there are some sign conventions. What are the sign conventions? When we trace the loop and direction of tracing your loop in electrical circuit is same as that of the current. If you are tracing the loop and in the same direction the current is flowing, then that potential drop is taken as negative. Suppose we are going to this loop, so such type of loop is there, A, B, C and D. Okay, here suppose some resistance is there, suppose R, and here it is some current I. So see, as we are going to learn, we are moving from A to B like this. This is direction of tracing the loop. Okay, so when we go A to B, in this is tracing direction, same direction current is flowing, then this potential I into R must be taken as negative. And another thing, suppose when we are tracing the loop B to C like this we are coming. Okay, this is R2 suppose, and this current is I2. Now the second case, when we are tracing the loop from B to C, up to down, but direction of current is opposite. In that case, that potential drop I2 R2 taken as positive. And these are the sign conventional for potential drop. Direction of tracing the loop is same as that of current, that potential drop is negative, otherwise it is taken as positive. That is nothing but for this potential drop. What about EMF? If we are tracing the loop like this, suppose this is positive, this is negative, we are going from down to up, D to A, and this is what? EMF E1 suppose. Then whether it is positive or negative, it will be decided that if direction of tracing the loop is like this, bottom to up, and if it start at negative, ends at positive, so this EMF is taken as positive. So you can write plus E1. Is that clear? If someone come from A to D, suppose A to D, when it ends at negative, then it becomes minus E1. Is that clear? In short, whenever we crosses the EMF, the last plate we get, that would be the potential of EMF. Suppose we go from bottom to top, last plate is what? Positive, so it is plus E1. If you are coming from top to bottom, last plate is negative, so it is minus of E1. That's it, that you must remember. Now in your book they have taken some diagram, and in that diagram they try to explain the same, just they try to apply the same to that diagram. I have plotted a diagram here a little bit side by. If you see, such type of diagram was plotted in your book. Now in this diagram, so there are how many loops that we have to consider? See, first of all, A, B, F, G, A. A, B, F, G, A. First loop. Second loop you can start with B, C, D, F, B. B, C, D, F, B. Second closed electrical loop. Third you can start A, B, C, D, F, G, A. We have started from A, we have again ended at A. Then and only then loop get created. Remember, suppose someone has started it little bit in different way. In that case, the loop cannot be applicable. What is that different way that we have to see? So see in this diagram, when I have started from A, B, F, G, A, it will form a closed loop. Suppose someone go like this, A, B, F, G. Whether we come to original position? No. A, B, F, G. This is not a loop because you must complete the circuit, then and only then it will be loop. So that is nothing but a Kirchoff's voltage law we have to applicable. Now here, that was a figure from your book 9.3. So let's start with the A, B, F, G, A for loop. For loop A, B, F, G, A. Let's see, starting point, end point must be same. Then and only then it will form a loop, otherwise not. So A, B, F, G, A. Let's apply the Kirchoff's voltage law. So as we are moving from A to B, this direction of current is same as a tracing the loop. What is that? Potential drop is negative. So it would be I1, R1 with a minus sign conventions. When we move from B to F, again direction of tracing is up to down, current is in same direction, again it is minus I3, R5. We move from F to G, current is moving in same direction, so it is minus I1, R3. Now when we move from G to A, EMF will move from minus plate to positive plate, so it would be positive 1. So plus E1 equal to 0. Plus E1 equal to 0. So this is the equation that we have applied for Kirchoff's voltage law. We have applied for the first loop A, B, F, G, A. I hope you understand this. If you don't, then let's take a second part also. You can take a second loop B, C, D, F, B. Let's see in your book what they have taken. Yes, B, F, D, C, B. They have taken B, F, D, C, B. Let's for loop. I will write again for loop B to F to D to C to B again same. So it will form a loop. Now we have to go from B to F, F to D, D to C, C to B. For this loop, what we can write? When we move from B to F, direction of tracing is same as that of current. So this would be minus what? I3, R5. I3, R5 potential drop. F to D, direction from F to D, current is moving same direction, again minus I2, R4. When move from D to C, last plate is plus, so it is plus E2. When we move from C to B, what is that? Direction of current is same as that of the tracing the loop, so it is minus I2, R2. Give homework to all of you. One homework. Just try to find. Now let's go to the next topic of our syllabus. That is nothing but a Videostone Bridge. Sometimes said to be Videostone Bridge because it was designed first time by scientist Videostone. Now what exactly it will use for, that we have to see. We know that in old days nobody knows how to measure the resistance. Unknown resistance was given to anyone. We want to measure that unknown resistance. For that, lot of scientists has prepared their own method. Videostone is one of them who has created the method to measure the unknown resistance by using bridge-like structure, and that is very well known at that time, and that is said to be Videostone Bridge. By using this Videostone Bridge, if you know the three resistors, then the fourth resistance can be determined easily. Now, as we know that the value of resistance of resistor depends on some parameter, environmental condition, just like it depends on the strain, humidity, temperature, displacement, that type of things. And we can measure the resistance from few tens of ohm to few hundreds of ohm by using this. Few tens of ohm to few hundred of ohm resistance can be measured by using this Videostone Bridge. What exactly Videostone Bridge is, that we have to see. So this bridge consists of, first of all, the four resistors P, Q, R and S. This P, Q, R and S are the four resistors connected in quadrilateral. This quadrilateral, every side has one resistance. This has a P, this has a Q, this has a R, this has a S. These are the four resistances connected on each side of quadrilateral, and the triangular part A and C, that this two diagonal A and C of the quadrilateral, they are connected to battery E, key K, and just connected the another terminal to another diagonal C. So this is nothing but a simple construction of Videostone Bridge. Videostone Bridge consists of four resistors connected in quadrilateral. Any one of the arm, in our case A and C, the diagonals are connected to battery through the key K. When we close the key, switch K is closed, current passes and it comes at A. At point A, current get divided into two equal parts. I1 along this branch AB, I2 along the branch AD. This is the current splitting. So you can write here one equation from this. Total current I equal to I1 plus I2. This is the first equation you can write at a point A. At a point A, current I came, it gets split I1 and I2. So you can write I equal to I1 and I2, and this is according to Kirchoff's current law. After that, current I1 passes to this branch, I2 passes to this branch. Now when current I1 reach to B, it will reach to point B. It can again split into two parts. Some part goes along this branch. Here G, this meter is G. G is nothing but what? Galvanometer. So current flowing to galvanometer can be represented by I suffix G. Remaining current I1 minus Ig passes from B to C. Remaining current I1 minus Ig passes from B to C. Same thing get occurred at point D. When I2 comes at D, at this point I2 plus this Ig comes and they move to the C. So I2 plus Ig move to this direction. So this is nothing but what? Simple concept. And again at this point, this current comes from here, that current comes from here, Ig get cancelled out, I1 plus I2 is I, again flow and goes to negative of the battery. So this is simple arrangement. Out of these four resistors P, Q, R, S, if any three are known, the fourth can be found out by using this Kirchoff's law. By using this Videostone network, and again by using Kirchoff's law condition. So what are the Kirchoff's law condition that we have to consider? So we have to consider here the closed loop. How many closed loops are here? A, B, D, A. I will write here A, B, D, A. This is the first loop, A, B, D, A. Apart from this, second loop is what? B, C, D, B. B, C, D, B. I will write here B, C, D, B. This is second loop. So these are the two loops here, independent loop. So you can apply here Kirchoff's voltage law to this loop. Now by using the conditions, I hope all of you remember, direction of tracing the loop is same as that of the current. It is taken as negative. If it is opposite, it is taken as positive. So start with the first A, B, D, A. A, B, D, A. For this loop, we have start from A to B. Tracing is A to B. Current is moving in same direction. So it is taken as negative. Minus I1 P. Now B to D we are moving. Top to bottom. B to D. Ig is moving in the same direction. Suppose G is a resistance of galvanometer. G is the internal resistance of galvanometer. Ig is the current. Direction is same. So minus Ig into G. Okay, we reach to B. Now we are moving from B to A now. D to A now, not a B. We are moving from D to A. Direction of tracing from D to A. Current is moving in opposite direction. So it is plus I2S plus I2S equal to 0. That equation we have written for ABDA loop by Kirchoff's second law, or that is said to be Kirchoff's voltage law. We can write this equation. Now let's go to the next part. This remaining part, the remaining loop BCDB. BCDB. When move from B to C, direction of loop is B to C, current is moving in same direction, so it is minus I1 minus Ig into Q. We reach to C. Let's go from C to D. Current is moving in opposite direction, so it is plus I2 plus Ig into R. We reach to D. Move from D to B. We are moving in opposite direction again. Plus Ig into G equal to 0. So these two equations we get. Suppose this is equation 2. Suppose this is equation 3. These two equations we get for two loops. Now what we have to consider in this case, suppose we have made this Ig equal to 0. Current flowing to the galvanometer is 0. Suppose, for sake of understanding, just imagine that current flowing to the galvanometer is 0. At certain condition, when current flowing to the galvanometer is 0, this bridge is said to be balanced. The bridge is said to be balanced, and that is one of the condition to use the Videostone network, the current flowing to the galvanometer must be 0, then bridge is said to be balanced, then you can apply the formula of Videostone network. Now let's start. What will occur when current to the galvanometer is 0? 0 into this G, it would be 0. This Ig would be 0. This Ig would be 0. Ig into G, this would be 0. Then you can write the another equation from this. You can write the another equation means further equation can be written from this. What are the further equation? By putting this Ig equal to 0, you can write here one thing. You can write here first equation, then we can write the second equation. So I can write this I1P equal to I2S, equation 4. Similarly, you can write from this the another equation, that is nothing but I1Q. This I1Q equal to what? I2R. Let us suppose this equation 5. Equation 4 and 5 we get. Now here in this case, divide equation 4 by equation 5. Divide 4 by 5. Divide करेंगे. Divide करो अपन मग बघूया. Divide equation 4 by 5. So divide equation 4 by 5. What we get? This divided by this. I1 cancelled out. We get P divided by Q equal to what? I2 get cancelled out, as divided by R. And this is the condition for Videostone bridge. This is the condition for Videostone bridge, and this is satisfied when current through the galvanometer is 0. Then the bridge is said to be balanced, and once the bridge is balanced, we can write P by Q equal to S by R. So out of these 4, any one resistance is known to you, you can find out out of these 4, any 3 resistance you know, you can find out the 4th unknown resistance easily, and that is the basic concept of using of Videostone network. So this is a Videostone network. Out of this PQRS, remember P by Q equal to S by R. P by Q equal to S by R. Apart from this, suppose I have rotated this quadrilateral by 90 degrees. Here A and C are here. After some time, if we take B and D here, if we take B here and D here, still the condition remains same. Only the instead of PQRSR, the value of resistance gets changed. That is the only difference. But still, the condition is same. When current to the galvanometer is 0, then we can say P by Q equal to S by R, and that is said to be Videostone bridge. After that, the Videostone bridge condition, and bridge is said to be balanced when current flowing to it is 0. So I hope that you get this Videostone bridge. Hello students, let's go to next topic of our syllabus, Videostone bridge, or it is said to be meter bridge. Now before this we have seen Videostone bridge or Videostone network, that we can see here. This part already we have finished. Videostone bridge it is said to be. Now if you consider, just we can modify this one. This is simple basic bridge created by Videostone. After that, this bridge get modified by the scientists, and it was just modified version is one of the device they have created which work on the same principle, and that device is said to be meter bridge here. So this is a meter bridge. Now it is said to be meter bridge because length of the wire used in this, it is said to be meter bridge because this is the wire AB, the darkened wire we can see. This wire AB whose length is 1 meter long. That's why it is said to be meter bridge. Is that clear? Along with this wire, the scale is marked. The scale is marked along with the wire, and to this wire AB, they have connected a battery, key, and rheostat in series with the wire AB. Apart from this, this meter bridge is said to be meter bridge. I have told you because length of wire is 1 meter long. Apart from this, it consists of 2 L-shaped metal plate. If you consider at this top, you can see this part. This part is nothing but what? This L-shaped metal plate. This again the L-shaped metal plate. So it consists of 2 L-shaped metal plate and third straight line metal plate, this one. So this side and this side, 2 L-shaped metal plate and one is straight line metal plate. They have arranged this plate such that 2 gaps are created. Left side gap is said to be left gap, right side gap is said to be right gap. And these 2 gaps are created, and here the 2 gaps are created by this central plate, and this resultant total device is said to be meter bridge. And here along with this, the scale is marked to measure the length of the wire. Now see, in Videostone network, we have the 4 resistors. Here, what are the 4 resistors? The first one is X. As its name is X, we know in mathematics, X is nothing but we want to find the value of X. So X is said to be unknown resistance, which we want to determine or find it out. X. R is a resistance box. It is a known resistance. You can change the resistance box. These are the 2 resistances you can see. But in meter bridge, we have the 4. So where are the remaining 2? So this wire itself can be divided into 2 parts. This is the first part. It has certain resistance. Second part, it has certain resistance. So it consists of 4 resistors. 1, 2, this up to AD, 1 resistors, 3, and DB, second resistor, 4. So these are the 4 resistors, and on this principle, this device work on the principle of Videostone Bridge. Here the galvanometer is also connected. Now let's start with this is the part of construction. Let's start with the working. When we switch on the key, the current flow to the wire AB. Apart from this, the resistance which is to be determined is connected to left gap, that is X, and known variable resistance box, that is R, is connected to right gap. After that, we have just connected to point C and D by the galvanometer. Between point C and D, there is a galvanometer, and this point D is nothing but what? It is a metal, just like a simple metal. That metal you can touch it at different portion of the wire. By that metal, you can touch the different part of the wire, and that is said to be jockey. Jockey is used to touch a different part of the wire. Now what is our aim? When we switch on the key, first of all, just hold this wire in our hand. Suppose I have hold it in my pen like this. Touch the jockey to the end A. Observe the deflection of galvanometer. If it goes to right side, touch it to B. It must go to left side. If the deflection is in opposite direction, then what can we do? Just do one thing. If deflection is in opposite direction, then just touch the jockey at different part of the wire and find out one point. Touch the jockey at different part of the wire. Find out the point D. Just touch it here and see the deflection in the galvanometer. If the deflection, when we touch at this point D, deflection in the galvanometer shows the 0, that means the point D is said to be null point. It is said to be null point. Null point means what? When we touch the jockey at this point, galvanometer shows a null deflection or 0 deflection. Then we can say current flowing through this galvanometer Ig is 0, because at this point the current flowing to galvanometer is 0 because voltage at C and D is same. Then we can say bridge is in balance condition. As Ig is 0, you can apply the Videostone network condition, and that we have to do here. And let us suppose the length of the wire AD opposite to the unknown resistance X, it is Lx. Length of the wire DB opposite to known resistance R is LR. Now we have to apply here the condition for Videostone bridge, because the bridge is balanced, because we have find out the point D on the wire AB such that when we touch it here, the jockey, galvanometer shows a 0 reflection, means current to the galvanometer is 0. Now what is the condition for Videostone network? P by Q equal to S by R. Same condition we have to use. X by R. So this X divided by R equal to resistance of wire AD, resistance of wire DB. Resistance of wire AD, resistance of wire DB. So this equation we get. Now while doing this, if you remember in 11th standard, we learn about the specific resistance. Specific resistance represented by rho, or sometime we can represent it by sigma also. So it is better to use sigma as according to your book. Specific resistance is represented by sigma, and that specific resistance sigma is equal to what? Resistance of the wire, resistance of the wire or metal, resistance of the wire or metal into area of that particular wire divided by length of the wire. If you remember, this equation already we have learned. So that equation we are going to use sigma equal to resistance into area divided by length. When we say just by using this equation, this R you can find it out. So find it out the value of R. So this equation implies that R equal to sigma into L. So this is sigma into L divided by A. Sigma into L divided by A. That we want to find out here. Sigma into L divided by A. Resistance we have find out. When we say it is a resistance AD, resistance across the wire AD, so it would be length of the wire AD. When we say it is about dB, just this is dB, the length should be dB. Okay, that are the correction only. Just put this value here. So RAD would be like this. Similarly, RDB equal to sigma into L length of the wire dB divided by A. Okay, what is length of wire RAD? It is Lx. So you can put that value here. Further, you can write the same equation as. Further, you can write the same equation here as. Just I will rotate the camera a little bit. So you can write this as sigma into Lx divided by A, sigma into LR divided by A. Because length of wire AD, length of the wire AD is Lx and dB is LR. Now put that values in this equation. Put that values in this equation. Rewrite the equation. So we can say this equation implies that X divided by R equal to what? Sigma into Lx divided by A divided by sigma into LR divided by A. This A cancelled out, sigma cancelled out. What we get? Lx divided by LR. From this equation implies X equal to, move this R to that side, Lx divided by LR into R. And this X is what? Unknown resistance that we want to determine. And in this method, the unknown resistance X can be find out by knowing the R. This is unknown known resistance, known variable resistance. So we know the value R. You can measure Lx, you can measure LR. So once you know this, you can find this unknown resistance X by using meter bridge. So this is simple method to measure the resistance which is unknown to you by using this device meter bridge, which work on the principle of Videostone network. Is that clear? I hope that you got this. Now before going into detail of the next topic, what exactly there is a in your book, there is some numerical. You can try to solve that numerical. Further on the next page 219, they have remember this. Within this diagram, there is a probability that there are some error can be created. What type of errors can be created in this measurement that they have given? So first error, when we use this type of wire lot of times, there is a probability that this wire may be uniform, may not be uniform. If the wire is uniform, then and only then you can find out exact value of unknown resistance. Because wire is uniform, you know the accurate value of Lx and Lr. But if the wire is not uniform, it is quite difficult. So the point to remember, cross section of the wire may not be uniform. If it is not uniform, it will create an error. Okay, that is first type of error can be created in this. Second, ends of the wire are soldered to the metallic strip where contact resistance is developed, which is not taken into account. While deriving this equation, see when we connect here, this metal plate we have kept on this metal plate, L-shaped metal plate. Here also the L-shaped metal plate kept on the wire, and it will create little bit much more resistance, and that is said to be contact resistance. That we have not considered here in consideration while deriving this equation. That is the second probable error. And third probable error, the measurement of Lx and Lr may not be accurate. The student or person who is going to measure this length Lx and Lr, that may be accurate, may not be accurate. If it is not accurate, then definitely value of X get changed. So there would be error in the measurement. So these are the probable error. First, wire may not be uniform. Second, contact resistance at the end point of this bridge. Third, Lx and Lr measurement may be accurate, may not be. If it is not accurate, there would be error. So how to overcome this error or how to minimize this error? So further topic to minimize the error, the value of R adjusted such that this value of R, we are changing this now, R. We can't change this, this is fixed that we want to find out. So this is a known variable resistance. Change the known variable resistance such that null point would always obtain between 34 to 66. This null point D should not go beyond this, it should not go below this. Then and only then the error can be minimized. Second thing, the experiment is repeated after interchanging the position. First 3 readings would be taken with the X to left gap, R to right gap. Next further 3 readings would be taken by changing the position. R can be shifted here, X can be shifted here. What it will do? It will minimize the contact error. Whatever the error here, same error when we move it here, it comes and they get cancelled out. And that is nothing but what? Interchanging the position of known and unknown resistance, we can minimize that resistance. Third one, jockey should not slide, it should be tap. Some students or some observer just slide it like this. Don't need to slide, just touch it. Tap it and find out a point T and up, move it up, again place it, again move it up, that is tapping. Tap it and find out a point D where galvanometer shows a 0 deflection. So these are nothing but a probable error and these are the probable solution for this. And apart from this, it's better if we use a wire AB having a uniform cross-sectional area. Let's go to application. Videostone bridge is used for measuring the values of very low resistance. If we want to measure very low value of resistance precisely and accurately, we can use a Videostone bridge for measurement of precise or very small value of resistance. Second, we can also measure the quantities such as galvanometer resistance can be find out, capacitance, inductance and impedance can be find out by using this Videostone bridge. We can find out capacitance, inductance, capacitance, impedance, galvanometer resistance can be find out. So these are some application of this meter bridge. Now apart from this, what they have mentioned, the next topic, actually they have not taken as a topic, but here in your book they have just mentioned observe and discuss. There is one topic in your book, observe and discuss. In that topic what they have done, they have used the method of Kelvins method, that is said to be galvanometer by Kelvins method. What is the Kelvins method that we have to learn in this? So meter bridge can be itself used in different way and that way is said to be Kelvins method. Now in this Kelvins method, what we want to determine? We want to determine resistance of galvanometer. To measure the resistance of galvanometer, what we will do? Little bit modification in the diagram of meter bridge. Just go to page number 1219, right hand side, there is the diagram. Now we want to measure the resistance of this galvanometer. So it get removed from here because this is unknown to us now. We want to find it out because it is unknown to us. So remove the galvanometer and connect that galvanometer here at the unknown place. So this would be the G, galvanometer. Okay, because we want to measure the resistance of this galvanometer unknown to us. Remaining whole setup remains same. Only another modification is what? Here we should not use a second galvanometer. There is one scientist who says, whose name is Kelvin, who says that it is not essential to use a second galvanometer, only single galvanometer whose resistance to be determined, internal resistance to be determined, that we can use. Directly connect the point C and D by the wire. Okay, no need of galvanometer here. That is said to be Kelvin's method. Initially, this point we don't know where it is. Just put it outside. So suppose this is wire, we can move it here along this part A to B by using jockey. Now initially what will occur? Initially when we switch on the key, this galvanometer shows some deflection without touching the jockey. This is jockey here. We have not touched it to any part of the wire AB. Still galvanometer shows some deflection. Whatever the deflection shown by galvanometer, keep it as it is. Okay, or you can adjust it, just rotating this rheostat, move it forward and backward, rotating them, you can take desired deflection in galvanometer. Once you get desired deflection in galvanometer, take this jockey, hold it in your hand, tap to different point of the wire, tap this jockey to different point of the wire and find out a one point D for which galvanometer shows same deflection or whatever the deflection initially when we have not connected it here. Suppose galvanometer shows a deflection of 10. It shows a deflection of 10. Touch the jockey at this point, it may shows 5, 12. Here it will may show the 10 because initial value is 10 when we switch on the circuit. Now it is again 10. So equal deflection. whatever be the deflection initially produced in the galvanometer, when we switch on the key, same deflection we get when we touch the point, when we touch the jockey to the point D. Then we can say this is the point D where deflection in the galvanometer is similar to initial value. So we can say point C and D are equipotential point. Means equipotential point means initially Ig is 0. Here there is no galvanometer, but the potential of point C and D is same. Bridge is said to be balanced. Bridge is said to be balanced. And that's why this Kelvins method is sometimes said to be equal deflection method. Initially, whatever the deflection 10 in the galvanometer, when we switch on the key, same. You have to find out the point on wire AB, the point D, such that at this point D, galvanometer again shows the deflection of 10 equal to initial. That's why it is said to be equal deflection method. Now, as equal deflection method, the bridge is said to be balanced. You can use our condition of Videostone network. What the conditions, we know that. Just put that conditions and just you can derive the formula. So you can write here G divided by R equal to. Now this length in front of galvanometer is Lg. The length in front of resistance is Lr. Just initially Lx we have taken because X is unknown. Now G is unknown, so it is Lg. So you can write this G by R equal to what? That same formula we have to use here. This formula, find the value of R equal to sigma L divided by A. Okay, so you can write resistance of wire AD divided by resistance of wire DB. Now you can put the values. What is the value? Suppose it is AD, it is what? Lg. Okay, and for resistance of wire DB, what is it? Sigma Lr divided by A. Put these values here. You can write this as sigma Lg divided by A divided by sigma Lr divided by A. A cancelled out, sigma cancelled out. So what we get? This equation implies that G divided by R equal to Lg divided by Lr. Our aim is to find the value of G. So this equation implies that G equal to R into Lg divided by Lr. So this is a formula to measure the unknown resistance G. Apart from this, we can modify this formula. Now see, what is Lr? This much length is Lr. The total length is 100. Okay, 100. So 100 minus Lg. 100 minus Lg is Lr. So put it here. You can write equal to R Lg divided by 100 minus Lg. So this is the formulas to determine the value of internal resistance of galvanometer by equal deflection method, or sometimes said to be Kelvins method. That's it. After that, there are 2 points they have mentioned: post office box, and after that Videostone bridge for strain measurement. Same concept they have used here. In the post office box, what we can say, they have just taken if you have the book, you can see the page number 220, left hand side there is one figure. From that figure we can just explain it. I will try to explain it on the book itself. So let's start. So let us see here, post box office. It consists of this type of circuit diagram. Here this is X, unknown resistance, and this S type of circuit is there. S type of circuit consists of 4 arms. So 3 arms basically. This is P. From this dot to this dot it is P. This is a Q section, and this remaining section is said to be R. 3 resistors, and X is the 4th resistors. From this diagram, P and Q are such that, as here they have mentioned, they have the values of 10 ohm, 100 ohm and 1000 ohm resistance in P and Q arm of this. And this R arm, there is a variation of resistance from 1 ohm to 500 ohm. Okay. While doing this, you can find this unknown resistance X by this method, and it is come to be here. Just on next page they have shown RQ divided by P. It is according to principle of Videostone bridge principle they have find out. Apart from that, if the length of the wire is L, you can find the specific resistance of that material, X into pi r square divided by L. X is what? Resistance, unknown resistance. Pi r square is what? area, L is what? Length, and that is according to this formula as we have just written here. So this sigma equal to RA by L. So R sigma equal to RA by L. R is a resistance here. In your book they have used X. A they have used in your book pi R square. Okay. So that is nothing but this topic. A they have used as a pi R square. So let's start here. If we go toward this topic, so that is nothing but the same thing they have mentioned here. So sigma equal to X means R, pi R square means area, L means the length. Now let's go further. The next application of this is what? Next application is here they have mentioned Videostone Bridge for a strain measurement. To measure the strain, we can use a Videostone Network bridge or meter bridge. So this is diagram for that. If you consider this first, second, third, and this is fourth resistance according to Videostone Bridge, with the Videostone Bridge condition. Now this what they have done at a fourth resistance. Instead of fourth resistance, what they have connected here? Strain gauge. Strain gauge they will connect. Remaining things are same. Already I have told you. You can connect AB to diagonal to battery or CD. This type of connections doesn't matter. So strain gauge is connected here. So whatever be the measurement done by this gauge, it is seen that its resistance get changed. If its resistance get changed, this resistance get changed, and accordingly there is change in the value of voltage across these 2 points. Galvanometer is there, initially you can connect here voltmeter. Whatever be the measurement change here, strain gauge applied for some measurement, its resistance get changed, it will change the value of voltage across these 2 points. Measure this voltage, you can find out the strain produced in that material or particular thing, and that is a strain measurement by using meter bridge. That's it. So this is the students only the topic that we have covered up till now that depends on Videostone Bridge network and meter bridge and its application. Next we will start with the potentiometer. Thank you.